Morning, everybody. So, do a simple, quick stream today. Answer any questions you have in science, the class, or science in general. And then, if there are no questions, I got a few little articles or research that was actually done on some black holes. So, we'll talk more about astronomy again later on in the year, but it's always kind of cool to take a look ahead or hear about some of the discoveries going on in the news right now. Because after last week talking about the coronavirus, talking about something different would be nice. Good morning, Azra. So just to kind of confirm with you, we are on a stream right now. Make sure, definitely, that you have the guiding questions and the hypothesis done for both the greenhouse warming lab and lab at the beach. We'll be finishing doing lab at the beach while we're collecting data on our little greenhouses. Hopefully there's some sprouting going on right now while we're not there. Won't know tomorrow either. There is no school. Hopefully Wednesday, kids M through Z, take a look, see what's happened. And then if you are all caught up, you don't have to do the guiding questions, you don't have to take care of the hypothesis, or you're not revising anything. I'll get into the DNA check number 6 in a second. Then you can go ahead and complete some IXL review on the water cycle. So the first link down here is the stream, the second one is to some IXL. You definitely turned into a distance learning god or goddess, whatever you want to call yourself, Azra. I do miss your sass. So DNA check, DNAC number 6, if you plan on revising, I just recently put that into Aspen. And if you plan on revising, then if I go up to classwork and I go to references, how to revise the DNA weekly assignment, you can take a look at this video. At about a minute in, minute 13 in, I go over how to revise the check. So in short, revising the check is going to involve you taking a look at the email I just sent to you, releasing your score, seeing which ones you got wrong. It doesn't tell you what the right answer is, it tells you which ones you got wrong. But in an email reply back to me through that form, it's not a bot. You can send an email back to that email that you got from Google about what you got on the check. You tell me what the right answer is, and a little bit of a justification. That means explain to me really well what the correct answer was, or eliminate the other wrong answers, and you can get some credit back on your check. And remember, the check and the sheet go together. That's the great you see in Aspen. Alright. Okay. Thanks, Azra. I appreciate it. See you later. Azra was a student last year on the Ducks. Nice to see the Ducks come back. So, about next week, or this week and next week, we are short a week, or these next 2 weeks again, because of Election Day Tuesday, and then we have Veterans Day the following week on that Wednesday, right, November 11th. So because we have 2 short weeks, what I've done, or what I'm going to do, is I'm going to combine. Let's kind of go over to the whiteboard. I'm going to, again, combine DNAs for this week and next week. So normally, let's go through like a normal week. Monday, Tuesday, Wednesday, Thursday, Friday. So a normal week, you would have DL, distance learning support, some review work, some revisions. Tuesday, you have DNA 1. Wednesday, you have DNA 2. Thursday, you can't use 2 days with the T's, so I made an R for Thursday. DNA 3, and then you have the DNAC, the DNA check on Friday, right? And the check is based off of your answers from the week. So that's a normal week, right? So what am I going to do for this week and next week? Well, so let's go through the next couple weeks. So this is for November 2nd, today. We got Monday, Tuesday, Wednesday, Thursday, Friday. So Monday today, distance learning, we're on a stream, we're doing some little review. Okay. Tuesday, there's no school. Wednesday will be DNA 1. Thursday will be DNA 2. Friday will be DNA 3. But when do we have the check? And we have a following week, right? So let's go to the week after. Not November 3rd. It's the week of the 9th. So next Monday is November 9th. Monday is still distance learning support, doing any kind of review, catching up. Tuesday, DNA 4. Wednesday is no school. Thursday is DNA 5. And then Friday is going to be a larger DNAC, a larger check. So a DNAC XL, extra large. So that means the DNAs from the previous week and then that week go together for the DNA XL. So 1, 2, 3, they're going to go into the XL. 4 is going to go in the XL. 5 is going to go into the XL. Okay? And what I'm going to do for that first week where they combine together, for the second, for today, this week, I'm going to make those first 3 kind of like a review of the water cycle. So 1, 2, and 3 are going to go together. They're going to be the same subject, if you want to think of it that way. So it's not going to be so much, I got to remember this, this, and this, of different types of things. Hopefully that week kind of blends together a little bit, so that if you know pieces of 1, 2, and 3, they kind of go together and are a good review of the water cycle. Okay? DNA 4, DNA 5, we'll talk about light and heat in a greenhouse, and then talk about plants and their role in the water cycle. So DNAs 1 through 3 are going to have the same overall kind of theme of talking about the water cycle. 4 will have its own theme, 5 will have its own theme, but all of it will go together in DNA XL. So normally on a DNAC, a check, it has 6 questions. Because there's 3 DNAs, I pull 2 from each. That means the XL is going to have, since there's 5 of them, 10 questions. Oops. Kind of messed all that up. Let me just get rid of it. It's going to have 10 questions. Okay? But again, 1, 2, and 3 are going to lead to a question that is going to be worth several points. All right? So I think for the most part, we'll be good in trying to remember over 2 weeks information that will go to a check. All right? You'll have your sheet, your notes. It's only really 2 extra questions. 2 extra DNAs, which means 4 extra questions, but there will be like a matching section that I'll talk with you more about. Okay? So I know I had a question about what does this week mean for DNACs and DNAs, so I addressed that. I had somebody asking about revisions, which is why, by email, which is why I addressed revisions in the first part of the stream. Okay? So I'm just replying back to question on Remind again about the check. Okay. So again, that was like a general question about science, the class, not about any science information. Again, if you have questions about science information, because you're revising something or you're working on IXL, let me know. It answers your question? Awesome. Yeah, I don't really want to do a check with only 2 DNAs. That's a very small check. 4 questions. You get one wrong, you make one small mistake, one simple error, you end up with a C, a 75. I don't like those odds. I like giving you guys opportunities. So, that means DNA week 7 XL is going to be worth, 1, 2, 3, 4, 5, 16 points. So, I mean, your odds are good on getting an A with 16 points. You can make a few more mistakes. I'm not good on my fractions, but, like an 8, no, a 12 out of 16, I believe that would be a C. So, you probably get a couple wrong and maybe still get an A, B+. So again, about the water cycle, about heat, the light of heat, infrared light, radiation, and then kind of talk about plants, because it's what we're doing the greenhouse warming lab. All right. The last check was about layers of the atmosphere. Those are going to become important to remember, especially when we talk about the water cycle with condensation. But yeah, I mean, it's a new topic, so that's why today's IXL is about the water cycle. Hopefully prep you for these DNAs this week. So if you got other questions, certainly let me know. But I did want to talk about some things that were found recently. So back on October 12th, I know that's not really recent anymore, but I found other things that kind of related back to it. All right, we currently live in a universe that's dominated by dark matter. It's matter that does not interact with radiation, doesn't interact with light, but we think it exists based on observations of gravity in our galaxy and in our universe. We see light bending around galaxies and stars. Gravitational lensing, we can see that with hypothetical clumps of dark matter. Galaxies, especially our elliptical galaxies, they rotate too fast. For as much matter as that they have, baryonic matter, matter that is us, interacts with light, they rotate too fast. Their energy should rip apart stars. So galaxies shouldn't really exist. There needs to be more gravity. And so we know gravity can be affected by distance and mass. Well, can't really impact the distance between stars, but we can definitely, go back to that equation and look at mass. So we see that there's more gravity exists to keep the shapes of galaxies that we see. So that means there must be some mass, some extra matter that we can't see. And so the scientists have been kind of looking for this dark matter different ways. Common way was to build things underground away from other radiation sources of energy, go down to the South Pole, create something that's very, very cold, a bunch of atoms in a little bit of a cube, kind of a crystal kind of arrangement, and any of these dark matter particles, they would bump into very cold particles because they're not moving very much. And all of a sudden, you got one of the particles in the cube move, boom. It was hit by something, And if it's not other matter, because you're away from other sources of radiation or other particles, could it be this mysterious dark matter? So the idea is dark matter is moving through you right now, through the gaps between your atoms. Because remember, atoms are mostly empty space. Could we set up an experiment to detect this dark matter moving through the Earth, moving through your body right now? And so it's been decades, but some scientists think they finally got a signal, a jump from one level of energy to another of one of the atoms used in their detector that could finally maybe be dark matter. Call it the xenon collaboration of scientists and their experiment. They used liquid xenon to look for WIMPs. Yes, a WIMP. What's a WIMP, Mr. G? Well, in science, a WIMP's an acronym. It stands for weakly interacting massive particle. So a WIMP is not somebody who's weak. In science, it's a weakly, well, it's kind of weakly interacting massive particle. So it's something, a small piece of matter that carries mass, but weakly interacts with the force of electromagnetism, which is where you're going to get light and magnets, and is one of the stronger forces in our universe. Gravity is the weakest, but it interacts with gravity of all the forces. So we want to know, as scientists, again, what is this thing? And there's been theories from neutrinos to exotic particles, but we've never, found what the dark matter is. So we got to find it, because our model of gravity, general relativity, understands that we need dark matter to be correct based on the observations of gravity. And so if we can't find dark matter, we got to rethink how we think gravity. And right now, that's like the ultimate goal of physics, is to unite general relativity and quantum mechanics. While general relativity works in very specific measurements and quantum mechanics works in probabilities, you can't combine something that works absolute versus, well, there's a chance of this happening. You can't put those two things together. Right? Exact measurements versus probabilities. So the goal is, both of them explain gravity really well, large scale, small scale. Can you combine them into one theory? And so, what are these WIMPs? So that's why we're so interested in them. So again, like right here, it mentions neutrinos, a byproduct of fusion in the sun's core. Could they be the possibility of providing dark matter to our universe? But then they could also be explained by an axion, which is, again, produced by the sun through interactions with electrons, photons, or nuclei. So a very exotic, one of those exotic particles. And I don't know if they talk about any other candidates. But here's a good connection, those of you in math, not so much algebra. A little scientific notation. The xenon collaborations, so the group of scientists who ran this xenon detector. Xenon's very cold at a liquid, so you want something cold because it doesn't have a lot of thermal energy, and so you want to make sure that any kind of bump, any kind of conduction comes from dark matter and not from something else, not from radiation, not from another type of matter, right? So this collaboration estimates that, zoom in, you can actually see it. I don't know what's up with this little bar on the right, but collaboration estimates that if dark photons, dark energy, again, also mysterious, energy and dark matter, were absorbed at a rate 10 to the negative 30 times smaller than regular light, regular photons, that could also explain the signal. So we're talking energy scales, tiny, tiny little fluctuation in energy, 10 to the negative 30. So if it was 1 times 10 to the negative 30, you got to move that decimal place over 30 times to the left, and you have 29 zeros in front of that 1. Incredibly, incredibly small decimal, small fraction, small amount of energy. That's how much this detector can actually pick up. So that's how cold those atoms are, right? Looking for very, very tiny changes in energy. Could it be dark matter? So that was just a cool relation to what we've been talking about in class. Happy election day? Yeah, happy election day. I know you guys aren't voting, but your parents, hopefully they go out tomorrow, or they have already voted. Just the civic duty. So again, this, if you want to read more, or you have questions on it, from the physics department over at the University of California, you can take a look at this link. This link is in the description. I think it's first. The next kind of story, since I got no other questions, I believe. Nothing on reminds. No emails. Nothing in the chat. Black holes. So 2 things about black holes. The first one, scientists recently, astronomers, saw a significant amount of energy, radiation, coming from one of the known locations of a black hole. And so they've traced it back and determined that they saw a black hole absorb a star, calling it a disruption event. So lots of energy flaring out from this black hole, and it happened 215 million light years away. So still within our galaxy. And remember, well, we haven't talked about a light year, but a light year is how far light can travel in a year, and it's about 6 trillion miles. Ooh, it's been a while. I don't remember if it's kilometers or miles. 1 light year in miles. Yeah, 6 trillion. It's about 6 trillion. 6 trillion miles. But you multiply 6 trillion by 215 million. Again, we're going to need scientific notation, huh? So it was visible in telescopes across the world, appeared as a bright flare of energy. Probably not all invisible light. Again, we've talked about light being in different forms. Probably ultraviolet, X-ray, gamma ray especially. Light that you can't see. As a star is sucked in, it undergoes a very scientific process called spaghettification. Spaghettification is a scientific term. Okay? In a black hole, gravity is more intense near the singularity, the center of the black hole, than it is at the event horizon, which is like the edge of the black hole. So you got to picture a black hole as literally a hole in space and time, to the point where it's a spherical hole, because space is, as far as we know, only 3 dimensions. 4 dimensions, there may be more. Still need observations on that, data on that, but if I can kind of move this out of the way, it's our dark matter. Really, a black hole has a singularity at the center, or if it's rotating, possibly a ringularity. It's probably a ring due to rotational energy. A hypothetical point of infinite density, infinite mass, and infinite gravity. Usually when you have infinities in science from math, you have a problem with your theory, with your math. You can't have infinity. And that's what happened with Einstein. He came up with this idea that there was infinities here, and he hypothesized a black hole. Well, you're not supposed to have infinities, but everything else has been observed to be correct in terms of gravitational lensing, time dilation, things like that. So black holes are an anomaly again in that you can't really explain them, or you can't explain the singularity through general relativity. You might have to do it through quantum mechanics, which again, black holes, high, big numbers of energy and gravity, but maybe explained with something very, very small. So it was singularity, and then around it is the event horizon. Okay? And the event, oh my god, that's so messy. The event horizon is the point where the escape velocity, the speed you'd need to escape the gravitational pull of the black hole, is faster than the speed of light. You know, nothing goes faster than the speed of light. So at that point, once you cross the event horizon, you're never coming back out of the gravitational pull of the singularity of the black hole. So usually we just think of a black hole as really the event horizon plus the singularity at the center. So we think of it like this, right? Both of these would be the same black hole. But because light can't escape, you don't see anything inside of it. Right? You see by light. So at the center there is a singularity. And so what happened is this star got a little too close to the event horizon. And its plasma and energy gets pulled in to eventually the singularity, and we'll never see the rest of the universe again. Spaghettification. Gravity is greater inside the event horizon as you move towards the singularity, and so the gravity at your, if it was you, at your feet would be greater than the gravity at your head. Okay? Black holes would literally spaghettify you, pull you, shred you from your feet up to your head. So it's kind of awful to think about, but it is a very scientific process. Alright? The idea of a black hole sucking in a nearby star sounds like science fiction, but this is exactly what happens in a tidal disruption event. So, star getting sucked in. We were able to investigate in detail what happens when a star is eaten by such a monster. And so this is actually a picture of the black hole that they got a couple of years ago. And what you're seeing here is kind of the edge of the event horizon. And you're seeing what's behind the black hole and in front of the black hole at the same time, which is kind of why it gets like this weird donut and disc shape going vertically and horizontally. Because the gravity is so intense, you see this accretion disk, you know, energy being sped up before the plunge into the event horizon, past the event horizon, and emitting a lot of radiation. So that star is going to create an accretion disk really around the event horizon as it's, you know, absorbed into past the event horizon to the singularity. So you're looking at the event horizon right there. So that is the event horizon of the black hole. The black hole itself, the singularity, somewhere at the center. A point, again, of infinite density, infinite mass, and infinite gravity. So you can't see a black hole, you can see the outline of the black hole. Well, let's take a look at their animation. Probably better than my doodles. Rare blast of light from a star was eaten by a black hole. So again, you're developing that accretion disk. This is becoming a quasar, these jets. So this energy is moving so fast that it just gets shot out both directions. It's not going past the event horizon, but it is going around it. And again, this is an artist rendition too, keep that in mind. Some of which falls in the black hole, but a lot of it will get shot out the north and south pole of the black hole. That energy is an all spectrum, an entire spectrum of light. So better animations than what I had. But again, it's very cool that we've actually been able to pick this up and observe it. So that was linked second in the description. And then this last one. What existed before our universe, if there was anything? What's going to exist after our universe, if anything? Sir Roger Penrose, who established the idea of a black hole from Einstein in theory and math, he says energy is coming out of black holes, and this energy was theorized by Stephen Hawking, which, if you know him, he recently passed away last few years. I think it's been a couple of years at least. I don't know, time goes weird in our situation, in our pandemic. I can't believe it's November already. But he believes that another universe will exist after this one, and he says that there's leftovers of a universe prior to this one. So if you look at radiation from deep space, the heat left over from the Big Bang, you could use the shifting of the light's energy down into lower energy states and use that as time, as a clock. And what you get, and we're going to talk more about this in astronomy, theory of the Big Bang and some other cosmological ideas, that the universe is about 14, 15 billion years old. So what was before the 15 billion years old, a billion years ago? You know, what's going to happen trillions upon trillions upon trillions, trillions to the trillions of power in the future? So Penrose, who recently won the Nobel Prize for his observations and evidence for black holes, he's kind of going on to say that the existence of unexplained spots of electromagnetic radiation in the sky, known as Hawking points, are remnants of a previous universe. So when we say that black holes don't lose energy, according to Stephen Hawking, that's a little bit of a misnomer, in that there are quantum effects at the edge of the event horizon, that there are virtual particles popping in and out of existence, popping in, annihilating each other, and going back to energy. So energy becoming matter, matter becoming energy. That was Einstein's equation, E equals mc squared. Energy equals mass times the speed of light squared. So there's a lot of energy in a little bit of mass, a little bit of matter. And so these particles are constantly popping in, annihilating, and then going back as energy. So we call these virtual particles. Morning, Beetle. So these virtual particles, they could happen right at the edge of the event horizon. So a particle pops in, particle pops in. Well, they should be identical, so let me just do that quick. But instead of being able to annihilate each other, this one has to fall into the singularity because it's in the event horizon, and this one is free to go. Whereas in normal space, these particles are popping into existence in the energy of the universe, and then they annihilate each other, and they go back to energy. And this is happening all over the universe. But at the event horizon of a black hole, one is inside the event horizon, one is outside the event horizon, one of them is sucked into the singularity, the other one leaves. And so what happens is, because this particle leaves the black hole, is able to leave the black hole, some energy is lost from that black hole. Some radiation is released. Yeah, you have to be on a non-school account for a chat. Thanks for letting me know, Trevor. So the black hole loses some amount of energy. And so the black hole, when it loses energy, it's going to lose that gravitational strength. So really, the event horizon gets a hair smaller every time it loses or is unable to capture the other half of this collision of particle, antiparticle, matter, antimatter, pairs popping in and out of existence. So black holes, in theory, according to Hawking here, says that black holes will evaporate over time. It's going to take such a long amount of time that Penrose here says that we see spots in the deep universe of just unknown heat, unknown electromagnetic radiation. And these unknown spots could be black holes that have evaporated or are evaporating from a previous universe. It just took so long for the black hole to lose energy over little pairs popping in and out at the very edge of its event horizon that it would take trillions upon trillions upon trillions of years, an unfathomable amount of time. So this is kind of part of a theory of conformal cyclic cosmology, that the universe behaves in cycles, that we go from a state of high energy, high order, to a low state of energy in very high disorder, and that would be entropy, what we've talked a little bit about in class. So eventually the end state of the universe is just a equal amount of energy distributed all throughout. It also requires mass to break down, which is not something all scientists are agreed upon, that mass, why atoms have mass, can just lose its mass. So black holes, in theory, may take so long to evaporate away, lose energy, get a smaller and smaller event horizon, have the singularity go away, that we may see Hawking points, where black holes used to be, where they've radiated away from the previous universe, if it existed. So how would a new Big Bang happen is still up for debate. Would the evaporating singularity explode because that's a lot of energy? Could that be the singularity be the seed of another universe because we think the Big Bang started as a singularity? Well, we have singularities in a black hole. What's really in a singularity of a black hole? Physicists don't know. So this is where a lot of research and a lot of theory is still being discussed in science. So we talked a little bit about dark matter. You have to use a detector that has no energy almost, as close to absolute zero as you can get it. Any impact, maybe that's dark matter, matter that does not interact with light. And we talked about black holes, things in the universe where they have gravity that is stronger than the speed of light, requires an escape velocity greater than the speed of light, which is impossible, which we saw a star get eaten by a black hole. And then these black holes do evaporate over time, in theory, according to Stephen Hawking, and that Sir Roger Penrose, who was awarded the Nobel Prize recently for observations of Big Bangs in the 70s and 80s, 1970s, 1980s, that they may evaporate, like Stephen Hawking said, and if they do, then we can call the points where black holes once were, after they evaporate, Hawking points, and maybe they're leftovers from a previous universe. So a lot of talk about radiation and heat, which is what we've been talking about in class. And we're going to talk more about black holes and the Big Bang cosmology and deep space as we go on into the year. So I don't see any other questions, or haven't received any other questions on reminds. Haven't got anything by email. Hopefully you're taking care of your labs if they haven't already been finished. That you can revise your DNA check. Return that back to you this morning. And anything is revisable. And a lot of the notes are in the agendas or videos that we had during distance learning. You can definitely take a look at the videos. You just got to go back to what you've missed. Go back to the days. All right. And if you're all caught up, got a few questions on reviewing the water cycle. All right. A lot of you have been doing the IXL, and you've been doing really well. So that's good in terms of the heat. Well, now moving away from heat, how about the water cycle? All right. So if you have questions throughout the day, you can send them my way. We talked about our black holes. So it'll probably be end of the stream. Hope you guys had a great weekend. Hope you stayed safe. Stayed away from people, but you still got some candy or had some fun. Okay? There is no school tomorrow. You don't have to do the attendance. Alright, but you should have done attendance today, and I'll be checking that pod too shortly if you're still watching. Okay? So you gotta do attendance today. Always for distance learning days. Tomorrow there is no school. I'll see you M through Z in person on Wednesday. A through L. Only get one day this week, but I'll see you in meets, I hope. Alright? Have a good rest of your day.